Hello, my name is Justin Bloom, and I wanted to talk about processor pipelining, a method of parallelism used in modern computers. First, to understand pipelining, it is important to understand what an instruction is. An instruction is a type of command the processor understands. They are binary codes stored in some sort of memory that tell the processor what to do. Most people write in a high-level language such as C, C++, Python, or Java. These languages are compiled or in some cases interpreted on the fly into machine code. Machine code is a group of instructions that make up a program. I've shown an example of a C language loop that has been translated into assembly code. I then translated the assembly code into machine code. As a side note, this is not optimized code but is written for simplicity. Older processors were only able to execute one instruction at a time. An instruction would be fetched from memory, decoded, and then executed. Then the next instruction would be fetched, decoded, and executed, and so on. The part of the processor that would execute instructions would be idle while an instruction was being fetched, and vice versa. This amounted to poor utilization of the processor's power. The clock speed would have to be slow enough to wait for the entire process. Some instructions, such as divide, were broken into steps, taking multiple cycles, but the next instruction couldn't begin till all the steps finished. Modern pipeline processors can execute multiple instructions at the same time. This is referred to as instruction-level parallelism. This is an example of a simple pipeline used by some ARM processors. An instruction is fetched. While it is being decoded, another instruction is fetched. While it is being executed, the second instruction is being decoded and another instruction fetched. This system allows three instructions to be processed simultaneously. It becomes more complex when values are loaded from or stored to memory because that process takes 4 cycles. In the example shown, the next two instructions after a load are delayed. The yellow squares represent stages where memory transfers occur. In this example, a memory transfer occurs during every cycle. However, in my next example, there are 3 successive load store operations. This causes further delays and causes a cycle where no memory transfer occurs. Another scenario that can cause complications is when a branch instruction occurs, or jump on an Intel processor. By the time a branch is being executed, 2 additional instructions are already working through the pipeline. If we move to another part of the program, the other instructions in the pipeline have become invalid, and there must be a way to effectively discard them. Now I will show an actual example using the processor I'm working on. This is shown using what is called a test bench inside of the Xilinx Vivado software package. Each row represents either a set of signals or a storage location in the processor. Most values are shown in hexadecimal form. Near the top is a value called address. This is the address of the current memory location being requested. Below it are the values coming in from memory. The one marked in blue is the first instruction fetched. It is a move instruction used to move a hex value of 12 into register R2. On the next clock cycle, the blue move instruction goes to another location to be decoded. The yellow instruction is fetched. It is an add instruction to add 8 to the register R2. Next, the blue move instruction goes to execute mode. The yellow add instruction goes to decode mode. Another instruction, shown in pink, is fetched. It is another move instruction, this time to move the value of 0 into R2. The green bubble shows that the hex value of 12 has been moved into register R2. The add instruction goes to execute mode, the pink move instruction goes to decode mode, and another instruction is fetched. This is a load instruction to load a value from the memory address in R2. The value at that memory location will be placed in R2. The green bubble is the result of the add instruction. 8 was added to 12, giving the register a value of 1A. The pink move is executed next. The blue load instruction is decoded and another instruction fetched. As a result of the previous pink move instruction, R2 takes a value of 0. As the load instruction is executed, the pipeline is temporarily stalled because of the extra cycle needed for load. Thus, the yellow instruction just fetched is not decoded. It goes to another holding location so that another instruction can be fetched. The address takes a value of 0, which is a value in R2, so the value at that location can be loaded. As the load instruction is executed, no new instruction is fetched. Instead, the value from address 0 comes in. This happens to be the machine code value of the first instruction we executed. The yellow instruction is now able to be decoded, and the pink instruction is stalled. The green bubble shows the result of the load operation. The value that previously came in is assigned to R2. The yellow instruction is next executed, the pink instruction decoded, and a new instruction fetched. In conclusion, pipelining better utilizes the entire processor. A single instruction actually takes longer, much like a single item in an assembly line has to take the time to go from person to person. However, since multiple instructions execute at a time, the throughput is increased. Pipelining makes a processor much more complicated, but it can greatly increase its speed.